Hi, this is the topic of functions. It's the second topic for the International Baccalaureate Mathematics Standard course. So in this topic, we're going to go through relations and functions. We're going to look at function notation, and then we're going to look at domain and range, composite functions, rational functions, and then finally inverse functions. So let's begin. A relation is a rule that shows the relationship between two variables. So for example, if a car is travelling at a constant speed of 60 kilometres an hour, then distance travelled and time taken have a definite relationship. And we can express it as y equals 60 times x. This is the distance here, is equal to speed times, and x is the time. Okay, so that's a relation. Now a function is a special type of relation where there is at most one output for any given input. So it's a little bit like a machine, or a black box if you like. So I've got some function f and it's transforming x's into 60x. Okay, and for it to be a function, it means that for any input that I put in, I'm only going to get one output, or at most one output. I could have no output, that's okay, but I can't have two outputs. So for example, if I put in x is 2, I'm going to get 120. I'm not also going to get minus 120. We'll look at this a little bit more in depth. So we say that y is a function of x, and we write it like this. Y is equal to f of x. That's how we say that. So instead of having y equals 60x, now we've got f of x equals 60x. It can also be written this way, and this says that the function f is defined as when x is inputted, it is transformed into 60x, or 60x is outputted. So the function f, x is inputted, it's transformed into 60x. It's also called a mapping. So f of x equals 30x plus 3 replaces y equals 30x plus 3. And it's just a more efficient way of doing our algebra. So for example, if we have f of x is equal to x squared plus 5x plus 1, we might want to find the value of f of 1. It's just basic substitution. I'm going to put x is 1 in here. So see, I have 1 squared plus 5 times 1 plus 1, which is 7. If I want to find f of negative 3, I would encourage you to put any negatives in brackets when you do this substitution, because we want all of that squared, not just the 3. So if you put that in brackets, you're more likely to get it correct. This means minus 3 times minus 3, which is positive 9. So 9 take 15 plus 1 is negative 5. Could also substitute in pronumerals. So instead of it getting simpler, we could make it more complicated. And I'm just going to substitute the 2a in where the x is. Again, I'm going to put that in brackets to make sure that I square both things, because this is 4a squared here. So it's going to be 4a squared plus 10a plus 1. Or, quite complicated things could go in. Again, put it in brackets. You'd have to expand this out and then collect like terms. Just have a look at that for a sec. Make sure you understand. I think this is the most important step, putting this in brackets so that you get every bit of it. Then we're just back to basic algebra after that and tidying it up. This is another way we can use it. So if f of x is equal to x squared minus 6x, for what value of x does the function equal negative 9? So instead of substituting in where the x is, this thing is going to become negative 9. So it'll look like that. I've actually put it over this side, but that's okay. Now tidy it up, it's going to be a quadratic, and it's actually a perfect square. X minus 3 all squared equals 0. So our answer is x equals 3. We could do a quick check here, put the 3 in there. 3 squared is 9, take away 18 is indeed negative 9. So I mentioned before that a function is a type of relation where there is at most one output for any given input. So let's have a look at function. So y equals x squared is a function, since for any value of x, there is only one y. It doesn't matter what number I put in here. So I could put in 7. 7 squared is 49. I could put in minus 2. Minus 2 all squared is 4. So there's only ever one output. So this guy's a function. This one's not. There's quite often, or quite a number of times where there are two values for y. Let's look at an example. Suppose I put in x is 9. So can you think of two answers when I square them will give 9? You can, can't you? There's plus 3 and there's minus 3. Both of those will give 9 when they're squared. So this guy's not a function. We can show algebraically that x squared plus y squared equals 1, for example, is not a function. And we do that by letting the input be some generic pronumeral, like a. So that's going in where x is, because x is the input. So a squared plus y squared equals 1. Take the a squared over the other side, and then do the square root. And here's our issue, plus or minus. So for quite a number of inputs, we're going to get two answers. Like for example, 0. If I put 0 in there, I've got plus or minus root 1 or plus or minus 1. So two answers for one input, not a function. One easy way to tell if a given relation is a function is to draw its graph and then use the vertical line test. So for example, this guy here would be a function, and that's because any vertical line that's meant to be vertical that I draw down through this function, it's only going to cut it at one place. Okay? And so this guy is a function. This one's not. Okay, there are multiple positions where I can draw a vertical line and it's going to cut in more than one position. Now something that I should mention, there's no such thing as a horizontal line test. So I might just get rid of some of these lines off here so we can see. There are various places through this that if I drew a horizontal line, I'd cut in multiple places. That's okay. Right? So it's only vertical. So for every input, these are the inputs along here, along the x-axis, at most there is one output. Let's consider this mapping below. So we don't really know what the function is here, if it is a function. But when I input 2, I get 40. When I input 3, I get 110. When I input 4, I get 200. When I input 9, I get 23. And when I input 10, I get 90. And that's it. So is it a function? Yes, it is. It's a one-to-one mapping. So I'm going from one input to exactly one output. What about this one? When I input 2, I could get 40 or 200. If I input 3, I get 110, 4, I get 200, 10, I get 90, and 9, I get 23. Is this a function? No, it's not. And the problem is 2. When I input 2, I could get two answers. Does that make sense? The input of 2 has two outputs. What about this one? So when I input 2, I get 40. 3, I get 110. 4, I get 200. 9, I get 23. And 10, I get 23. Is this a function? Yes, it is. Okay, it's okay to have two different inputs that have the same output. All right, that doesn't break the rules of a function. When we define a function, we state the domain for which the function is defined. And the domain is the set of values for x for which the function exists. A domain can be restricted. We will go through that later on. But if it's not specified, then we just use the natural domain. I'll show you what I mean. So for example, the line y equals x plus 2, it has a natural domain of all real numbers. So what I mean by that is this line stretches in either direction to infinity. So in terms of x coordinates, it's always going to exist, all the way out here and all the way in the positive direction. So the natural domain is all real numbers. This is what we write. So our function y equals x plus 2 is defined for all x such that x is an element of R, and R of course is the real numbers. Now if we restrict the domain, suppose I just want to give this part here of that line, this interval, then we would write this. Our line y equals x plus 2 is defined for all x such that negative 5 is less than or equal to x is less than or equal to 3. So we would give that interval. You might get asked to state the domain of the function of a particular function, like this question. State the domain of the function y equals the square root of 9 minus x squared. Now that's a semicircle, which you may or may not recognize, but if we put it on the graphics calculator, we get this. So basically what we've got to do is state the values of x for which the function exists. And we can see it exists between negative 3 and positive 3. So we're going to write this. The domain is all x values such that it lies between negative 3 and positive 3. Range refers to the set of y values for which the function exists. So same question, but now we're going to state the range for y equals the square root of 9 minus x squared. So here's the picture. Let's have a look at the y-axis. It goes between 0 and 3. So can you think what we need to write? In curly brackets, y such that 0 is less than or equal to y is less than or equal to 3. Let's have a look here. We want to state the domain and range of the function shown. It's a hyperbola. The dotted lines are called asymptotes, and that means that the curve gets closer and closer to those dotted lines but never cuts or touches it. So this means that in terms of the domain, this function is going to exist everywhere along here and everywhere up here except that point, positive 3. Same with the range. It's going to exist everywhere down here and everywhere up here except for that point, negative 1. So this is what we will write. The domain is all values of x such that x is not equal to 3. And the range will be values of y such that y is not equal to negative 1. Now this is called a piecemeal graph, and you can see it's got bits and pieces. It goes here from negative 1 up to positive 1, and then all of a sudden jumps up to 2, goes up to 3, and then is flat onto infinity. So it is the function y equals x between negative 1 and 1, but not including 1. And then it's the function x plus 1 between 1 and 2, but not including 2. And then it's equal to 3 when x is greater than or equal to 2. Let's have a think about how we might state the domain for this. So we're thinking about the x values. It obviously doesn't exist here. It exists between negative 1 and positive 1, and it actually does exist at positive 1 because it's up here at 2, so that's okay. And it exists all the way along and up to infinity. So we're going to write the domain is x is greater than or equal to negative 1. So everything from this point upwards. What about the range? We've got a bit of a problem with the range. It doesn't exist down here, obviously. It exists between here and here, but not including 1. Nothing in between 1 and 2, and then from 2 to 3, and nothing above. Let's see how we write this. So it's between negative 1, including negative 1, up to 1, but not including 1. And then it jumps and includes everything between 2 and 3, including both of those numbers. Okay, does that make sense? Sometimes we have to find the domain and range just from an equation, like this one here. I actually don't know what type of function that is. It's not one of the typical ones. I could use my graphics calculator to look at it, but remember there's a whole paper where we're not allowed to use the graphics calculator. This would be a typical question that they would ask. What we're going to do is do this algebraically. I know there can't be a negative under the square root. So therefore, the thing that's under the square root has to be positive. That's actually the domain there. I've just got to tidy it up a bit. We want it in terms of x, not x squared. So we need to solve that x squared minus 1 is greater than or equal to 0. And I'm going to use a sign diagram. The critical points are plus and minus 1, because both of those will make 0. So I draw it up. And now I'm going to test some points in these 3 positions to see whether they're positive or negative. Okay, let's test negative 2, 0, and 2. Let's start with 0 because it's easiest. 0 take 1 is negative 1. Is negative 1 positive or negative? It's negative. All right, let's test negative 2. Put negative 2 in there. Don't forget your brackets. Negative 2 all squared is 4. 4 take 1 is 3. Is 3 positive or negative? It's positive. And then finally, let's test 2. 2 squared is 4, take 1 is 3. 3 is also positive. All right, looking at my equation here, I want when this thing is positive, so that's here and here. Let's write the domain. X is less than or equal to negative 1, or X is greater than or equal to 1. Now finding the range is a little trickier. It's not quite as intuitive. We know that this is the positive square root. We can tell that because it doesn't have a negative there. So it's got to be greater than or equal to 0. And there actually is no upper limit. Okay, any number I can put in here, it's just going to get bigger and bigger. I could put 4 million in, and that would be okay. So it's actually a fairly easy range question. It's going to be everything greater than or equal to 0. And there it is. Here's another example. State the domain and range of f of x is equal to 1 on 1 minus x squared. Okay, again, not really sure what this graph looks like. Could put it in the graphics calculator, but I need to know how to do it without doing that. Our issue is going to be a denominator of 0. So basically, this function is going to be fine, providing the denominator doesn't equal 0. All right, let's figure out when that happens. So 1 minus x squared cannot equal 0. Taking the x squared over the other side, x cannot equal plus or minus 1. That's the only issues. So our domain is all values of x such that x is not equal to plus or minus 1. Now with the range, it is tricky. You kind of got to think backwards. Now we know that there's problems with x being plus or minus 1, and this denominator can never be 0. All right, that means that this whole fraction can never equal 0. Now just think about that for a second. If I can't get a 0 out of 0 on the bottom, which we can't because that's infinity, there's no other way to get 0. Can you see that? Doesn't matter what number I put in this x, this fraction can never equal 0. So that means the range will be everything except for y equals 0, which we write like this. All values of y such that y is not equal to 0. Here's another example. Find the domain and range of f of x is equal to x plus 1 over x minus 2. Let's start with the domain. It's easiest. What's the issue? The denominator can't be 0, remember? So I'm hoping you're telling me that x equals 2 is impossible. So therefore the domain is all values of x such that x is not equal to 2. That's the easy part, the range. In this case, we can get a 0. Negative 1 is fine. If you put negative 1 in here, the numerator will be 0, and a numerator of 0 is fine. Okay, so we can't use the same method that we used. I'm going to show you a tricky way of doing this. So to find the range, we're going to split it up into 2 fractions. What I'm going to do is match the denominator up top. Have a look at this. Okay, so I've matched that. Do you see how that's the same? And then I've sort of fudged it, if you like, to make sure that I haven't changed it. This is x plus 1. This is still x plus 1. Do you see that? Okay, so this is just a technique to be able to find the range. So I've matched the denominator and then fixed it up so I haven't changed anything. Now I'm going to split this because it is now a top-heavy fraction. I'm going to split it into 2. X minus 2 on x minus 2 is 1, plus 3 on x minus 2. All right, stare at that for a bit and make sure that makes sense to you. All right, you might be saying, how on earth do you find the range from that? This can't be 0. Okay, we've got the same question virtually that we had on the previous slide. If I put a 2 in there, I get a 0 on the bottom, and that's no good. And I can't make the numerator 0. So that can't be 0. So f of x, or y, can't equal 1. There's the range. Okay, that might blow your mind for a bit. Let's just go through it again. I've taken this, I've matched the denominator, and fixed up the top so that it's the same as what it was. Split it into 2 fractions. Now that I don't have an x on the numerator, I can't get 0 there. I can't get 0 on the bottom either. That thing never equals 0. Therefore, if that's never 0, this thing is never 1. Alright, so that means the range is y is not equal to 1. Now suppose we're given two functions, f and g, then we define the composite function, which looks like this, f with a little circle g, as f of g of x. That's probably the best way to learn it, f of g. Let's look at an example. So find the composite function if f of x is equal to x squared plus 1 and g of x is equal to 2x minus 3. So we're going to take this f, and instead of the x, we're going to put g of x in there. Can you see that? So we're going to put 2x minus 3 in there. And there it is. That, of course, just means that instead of x, we put 2x minus 3. So we're going to expand that out and then tidy it up. And that's it. Now, f of g is not the same as g of f. Okay? So they are different things. Don't assume that they are the same. Let's have a look at one. So find f of g of x and g of f of x. If f of x is x squared plus 1 and g of x is 2x minus 3. So we've already found the first one. There it is. Now we're going to find the reverse. So it's going to be g of f. So instead of the x here, I'm going to put x squared plus 1 in there. So that'll go in there. Tidying it up, and I get 2x squared minus 1. So yeah, they're not equal. Now a rational function is the division of a linear function by another linear function. Do you remember what a linear function is? A straight line. So if we've got two straight lines like x plus 1 and x minus 3 and we do the division, we're going to get what's called a rational function. This is also a hyperbola. That's the graph of it anyway. So typically rational functions will have asymptotes. We talked about those in a previous example. An asymptote is a line that the function approaches but never touches. Now the graph of a rational function is called a hyperbola, and it consists of two asymptotes. They are along the axis in this case, that are at right angles to one another. This is actually the graph of y equals 1 on x. So it's a rational function, that's a straight line, and that's also a straight line. How do we graph something like this though? Remember this guy, x plus 1 over x minus 3? We're going to do that same method that we just did before. So I'm going to match this denominator up top and then fix it so that it's still equal to x plus 1. Have a look at that. X minus 3 matches, plus 4, x minus 3 plus 4 is x plus 1. Now I can split it into two fractions. Becomes 1 plus 4 over x minus 3. Okay, where are the issues? They're the asymptotes. Here, x equals 3 is a problem. Cannot equal 3. And this whole thing here can't equal 0, so y cannot equal 1. So there's the other one. Okay, so when we graph it, it's going to look like this. Asymptote here at y equals 1, another asymptote here at x equals 3, and there is the hyperbola there. Okay, we're up to the last bit. An inverse function is one that undoes a function. So it's denoted by f with a little negative 1 up the top. You would have seen this before with inverse operations. So plus and minus undo one another, times and divide, square and square root. And the one place that you've seen this little negative 1 is on the calculator when you look at inverse sine and cos and tan. So just above the sine, cos, tan buttons, you'll see sine with the negative 1, cos with the negative 1, and that's what you press when you want to find an angle. So you're doing the reverse. So that's what this is as well. It's like this. If you've got a whole bunch of apples going into a function box and they come out as lemons, and then they go into the inverse function box, they'll come back out as apples. So it undoes the function, if that makes sense. Here's another example. If I'm mapping from ABC to 1, 2, 3, then the inverse function will map from 1, 2, 3 back to ABC. So let's bring it back to talking about the algebra. The relation or function obtained when we interchange x and y, so wherever x is I put y and wherever y is I put x, is x is equal to f of y. We're used to y is equal to f of x. So if I change them around, I get x is equal to f of y. if for each x in that domain y is unique, then this will represent a new function that is called the inverse function. So I switch x and y, and if it is a function, then it's going to be called the inverse function. So the relation x is equal to f of y is only written in this notation, f to the power of -1, if it is a function. And it won't always be. We'll see plenty where it's not. Here's one. X is equal to y squared is not a function. Here's the graph. Do you remember the test for a function, the straight line test? It's cutting in two places. Okay, so it's not a function. So we can't write it using this notation. A function and its inverse are symmetrical about the line y equals x. That's because you're switching the y and the x. Okay, so any function, you can see here the blue line. If I want to find its inverse, it's going to flip over that line y equals x. So suppose we want to sketch y equals 2x minus 1 and its inverse function. We could just draw up the line y equals 2x minus 1. So it's cutting here at -1, goes up by 2 and across 1. Here's this dotted line here is the line y equals x, and all I'm going to do is reflect it across that dotted line like this. So there's the inverse function there. Here's some examples. What's the inverse function of f of x is equal to x plus 2? So first thing we've got to realize is that this f of x is y. So we're going to switch the x and the y like this, and then we're going to make y the subject. And that's pretty easy. Y is positive here, so I'm going to leave it and just bring this 2 over the other side. I'm going to switch it around at the same time, if that makes sense. Now this is a straight line, so therefore it is a function. So I can write it as f to the -1 of x is equal to x minus 2. Now, remember before I said that inverse functions will undo the function. So let's have a look at how that works. Suppose I substitute in x is 5 into this function. Well, that gives me 7. So if I put 7 into this one, what happens? I get 7 minus 2, which is equal to 5. Okay, can you see how that works? Let's look at this one. F of x is equal to 4x. So start off by realizing that this is y. Switch them around, x is equal to 4y, and then make y the subject. That's also a straight line, so it is a function, so I can write that as f to the -1 of x is equal to x on 4. Here's another example. F of x is equal to x cubed. So this is y. Switch them around. I get x is equal to y cubed. Now I need to make y the subject. I'm going to switch it around and do y cubed equals x. But how do I get rid of a cubed? I've got to do the cube root. Do you remember that? Of both sides. Okay, so y will equal the cube root of x. Now in this case, a cube root will look like this. And it is indeed a function wherever I draw a vertical line. So I can write f to the -1 of x is equal to the cube root of x. And then finally, the one we just did before, f of x is equal to x squared. When I switch this around, I get x is equal to y squared, but when I make y the subject, I get y is equal to plus or minus the square root of x. And it looks like this and is not a function, so I can't rewrite it. I can't write this next line that says f to the -1 of x, okay, because it's not a function. Cuts twice in a lot of places. Now when we swap the x and the y, if we get a relation and not a function like we just did, what we can do is restrict the domain to make it a function. So we talked about this earlier in the video. So here's our little friend here, y equals x squared and x equals y squared. It is not a function when we do the inverse. So y equals x squared, switch it around, we get plus or minus the square root of x. So if I restrict the domain, and I'm talking about this orange parabola here, if I restrict the domain to be just x is greater than or equal to 0, so everything over there, then when I flip it over, I get this part. Okay, so let me just grab a pen. I won't have this bit here then, or this bit for that matter. And so it will be a function. So therefore, in this case, the inverse function will be this positive, I haven't written that there, but you don't have to, the positive square root, where the domain would have been x is greater than or equal to 0 and the range is y is greater than or equal to 0. Now there's a curious thing about domain and range with inverse functions. The domain of f of x is equal to the range of the inverse. And the range of f of x is equal to the domain of the inverse, so they switch around. Let's have a look at an example. So here's a function. It's actually an exponential, but I'm not going to go into what its equation is. And you can see here there's an asymptote at -2. So the curve gets closer and closer and closer to -2, but never touches. So our domain for this function is all real numbers for x, goes forever in both directions, but the range only goes down to -2 and never touches it. So y is greater than -2. So if I flip this across the line y equals x, we get this orange curve. Let's have a look what's happened. So now, can you see how the domain stops at -2? There's nothing over here. So our domain is going to become x is greater than -2. And what about the range? Goes all negative numbers. Actually looks like there might be an asymptote here. I haven't shown you enough of the graph, but there's not. It goes up and up and up to infinity. So it's going to be all real numbers for y. So our range will be y is an element of the set of real numbers. So you can see how they've switched. So remember that we said that the composite functions f of g of x and g of f of x are not always equal. Well, if f and g are inverse functions, then lo and behold, they are equal. Let's have a look at this. So in this example, we want to show that f of inverse f is equal to inverse f of f for this particular function. All right, before we can do this, I need to find the inverse function. So let's just do that quickly. Switch it around, tidy it up, and make y the subject. It is a function because it's a straight line. Okay, so here's our inverse function, and here is our ordinary function. So let's start with this guy. So this is f of inverse f of x. So into f, which is here, I'm going to put the inverse function. So this guy here is going in where x is. Hopefully that makes sense. You can see how I've done that here. When I tidy that up, can you see how these 2's cancel out and I get x minus 1 plus 1 is equal to x. All right, now let's do this one. So into inverse f, or f to the -1, I'm going to put f of x, which is 2x plus 1. So the 2x plus 1 is going to go into here. So it's going to go in there. Can you see it? 2x plus 1. All right, plus 1 minus 1, that's 0. 2x divided by 2 is equal to x. Okay, so they're equal. Can you see that? And this is no coincidence either, that this came out to be equal to x. I'll leave you to think why that might be. All right, a couple of things just to finish off. The function y equals x is called the identity function. So it maps a function to itself. Okay, so whatever you put in, if you put apples into the function box, you get apples out. So that's why it's called the identity function. And this is how we would write it. We would define the function f such that x maps to x. And then finally, self-inverse functions. They are themselves symmetrical about the line y equals x. So if you do the inverse, you get the same function, if that makes sense. So for example, the following functions are self-inverse functions. Y equals 1 on x, and y equals x, there are 2 of them. And in these cases, the function will equal the inverse. So just having a look at this first one, y equals 1 on x, if we drew up its graph, it's a hyperbola, it looks like this. And if we drew the line y equals x through the middle there, you can see how it's symmetrical on both sides. And when we switch these two around, what do we get? X is equal to 1 on y, which switch them around again and you get y is equal to 1 on x. So they're just self-inverse. Okay, that brings us to the end of this topic.